I will try to explain this to you as detailed as I can because there are a lot of tricks that we have done when we are removing things. So first of all, let me write you our function. So there was a remove function, okay? And in this remove function, we were calling the, what was it? Find parent function. Okay. So what this find parent was supposed to do was, okay, if you have got a tree like this, and you would like to remove one of its nodes, then it returns you the parent. This is what we know. But now we also want to add a new functionality. We want to get a reference to the child that is being removed from the root node, or from any of the nodes in here. So it's like, it might be the case, let me draw this bigger. Let me draw this even bigger. So let's say this is the root node of me, and there are nodes in here. So if that is the parent, it might be the case I am deleting this node or this node. Okay, so it changes according to which node is being deleted. So this is a reference to this node, and this is a reference to this node. So how we will represent this one as a class node, right? And in here, there is node pointer left, and there's node pointer right. Okay, so if you look at this one again, how it looks like in the memory, let me draw you the memory. Okay, so this is our memory. And in here, there is the object, the node's object. This is the, let's call this one root, okay, or parent for better. Okay, and inside the par, it looks like this. So there is this data, 3, 4, 5, whatever it is, and there is this address. Let me draw it a little bit larger. So there is this address ABC, and there is this address DEF, and also this ABC and DEF are pointers to some other objects. Okay, so this is the left tree. So this is actually this guy over there, and this is the right tree. And this one is actually this guy over there. Okay, and their address is ABC and DEF. And this ABC and DEF pointers in memory, they have their own addresses. So let's call these 010, 020. Okay, so now the memory looks like this. So what I want to do is, when I call find parent, since I cannot return two values from the find parent function, I am going to send a parameter by reference, and I want to put inside this parameter by reference the address of this. Okay, so I want to return 010. Why? Because what I will do is I am going to update this one over there. Okay, update this address. So if I return the address itself, then it's not going to be the contents of this particular memory cell. You know that we have talked about calling function, sending parameter to function, returning something from the function. It will be actually the copy of this address. If I return from the address from the function, so it will be I will be able to dereference it, but I won't be able to update this value in here. In order to be able to update this value in here, I need this guy's address over here. Okay, so I need this address, and this address is of type, for instance, let me give you an address in here. Let me call you 002. The 002 is of type integer pointer, right? Because it holds integer inside. So this address is integer pointer. What about this? This guy holds an address to node. So it points to node pointer. So this is double pointer. Okay. So node double pointer means, first of all, integer pointer means this is the address of a memory cell which holds an integer inside. This means this is an address of a cell which holds node pointer inside. Not node itself, but node pointer. Okay. So that's why I need to have a node pointer. And I need to return it back. So what I do inside here is I actually get, there's some kind of a parent I have found. So I am going to get parents left child, and I do not get the left child itself because that will return me this ABC thing. I need to take the address and return it. Okay. But we have also run into a problem doing this, and I'm going to explain it to you. But just now, know this. Okay, I'm going to get the parents left, and I'm going to return it. So what am I going to have? Imagine I'm doing the remove, and I need a node star star, right? N P T R, and when I call find pointer, it's going to fill in that one. So if I was returning from the function, and if I was returning this value from the function, then just having a double pointer would be sufficient. But what am I doing is I want to call the function, so find parent. I want to send in an empty pointer, n pointer, and I want this one to be filled in inside here. Okay, so when I send it in here, I want that to be filled in here. So let me continue to draw my memory. So in my memory down there below, I have defined a node star star n pointer. So this is, it is going to keep an address, okay? And it has got its own address, like F00, okay? And this address will be the address of a node pointer, because this is node pointer. Now, if I call find parent and directly send this, what is going to happen is the contents of this guy is going to be filled into a new address and will be pushed to the stack to be received by the function and updated. So if I do this, when this function runs and fills this in, it will go away once the function finishes. The original, this guy over there, will not be filled in. So it's like just like sending an integer. So integer's copy will be sent, and the original integer will not be changing. Now, what I need to do, I need to send a reference to this. Oh, I'm sorry. To this guy over there, to here. So the reference to it is this. And what it holds node pointer, and the address of a node pointer will be node triple pointer. Okay, so actually you shouldn't think of it like a triple pointer, nest pointer, but it's an address, and I know who this address belongs to. It belongs to a node pointer. So it's the address of a pointer which points to another pointer which points to node. Okay, in theory, when it's being calculated. But to be more clear about this is you can think of it like this. There is going to be an address in here which I didn't yet initialize. Okay, and what am I doing is I'm sending the address of this guy's address. So that's why I send an ampersand in here, and when I'm receiving it in here, I put triple pointer. So node triple pointer A. Now what does this one refers to is there is a variable here called a. It has got its own address, but it's not very important. And inside this a, f00 is written. Okay. So what it points to? A double pointer of a node. It will hold the address to this guy over there, double pointer of a node. Okay. All right. So what do we do? Well, we send it. So, and then we do like here, star A equals this. Why? Because I'm going to write the parents left, which is like this in here, the 0, 0, 1, 0 over here. I take this one and I write it in where the A is pointing to. A is pointing to here, so I write here 0, 1, 0. Okay. So now what does this one hold? 0, 1, 0. When this function find par ends, this is going to go away, but this will be still present inside the remove function. So since I got this one inside the remove function, now I can use it. And how I need to use it when I want to do something over the nodes pointer, I need to, of course, again, dereference it, because now this one shows me this, okay, ABC. If I say, for instance, the m pointer equals blah, 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 then it means I'm actually writing some stuff in here, which means I'm changing inside here. Okay. So what is this burden about? Why am I doing all these things? The answer is simple, because I don't want to do like if the removing node is the left node, then do this. If the removing node is the right node, then do this. Do the same stuff actually, but twice. So I don't want to do this. That's why I'm going through all this trouble. But on the other hand, you might think of like, well, let my code be 4 lines longer and more understandable instead of doing pointer magic. So you can, of course, do this, and it doesn't matter. But this is a good exercise for understanding pointers, so I'm doing this. So this is actually what we have done. There is also one more thing which is related to pointers that we, a trouble that we ran into, and it was like, it was about this. Okay, so we don't do like, give me parents left pointer, left child, and it directly gives you the pointer's address. Okay, it doesn't work this way, but what I did naively is I called the parent get left. And I tried to get the address of this, but it was a stupid thing to do. Why? Because when I call parent get left, what has been given to me is, again, my memory continues from here. What has been given to me is, actually, when this function is called and it ends, it returns me the value of this guy over here, 0, 1, 0. Yeah. And the cool thing is, I'm sorry, not 0, 1, 0. It's A, B, C, whatever is written in here. So it returns me A, B, C. But how it returns me is not in its original memory address, so that I cannot dereference, I cannot reference it and get the right memory location. But what it does is, when returning, it pushes it to the stack. So the pointer is the same. When I dereference it, I get the node. But since it's in the stack, its address is something not meaningful to me. And even C++ is not letting me to take the reference, because it's something inside the stack. It's not this memory location. Okay, so when I say get left, it returns me the pointer, but the pointer is just a copy of the original pointer in another memory, in another place in the memory. So when I say parent get left and take the memory address, it says, no, I cannot do this. It's somewhere in the stack. I won't give you this. Okay, so this is pretty awesome. I think without knowing, we actually have a very good demonstration of how the function calls pointers work. I hope you are able to understand what's going on in here. So that's why instead of doing this, I have written a new get left memory kind of get left address kind of thing. And what this returns is the ampersand, the reference, the memory address of parents left. But what it does is it doesn't do it with a function call. It directly gets the parent left address and returns it to me. So now I got the right address. All right. So this is what went on in the morning session around 12 o'clock. But we were able to manage it and write our code. Now I'm going to finish that code. I can have any questions if you have. Well, that's actually a lot to digest, but please try to understand it as much as possible by going over. It would be very understandable when somebody explains it, but in the field, when you run into that, it might be a little bit tricky to understand what's going on. So you should think about it deeply. Okay, now we have done all this and our test was running good, I think. But if I remove something which is not there? But it's easy, right? So it will just directly go out. Let me check. What is bad? Oh, there's something. I made some changes. I added some spaces to make it more easily understandable, and of course that caused the problem. Yeah, it's going good. I've got the correct thing. I didn't have any memory leaks. As far as I can see now, what's left is I only need to remove the root. If I am removing the root, what am I going to do? So this remove thing, so if I've got a null, all right, what am I going to do? Yeah, so if, oh, I'm sorry, if my parent is null, what am I going to do? So this is going to be else. Okay, so if parent is null, which is I'm deleting the root, what should I do? What should I do is this root, again, I need to check if the left is null or not. If this root get left is not null, I need to do something. Else, if it is null, now my job is the easiest in here. So what I need to do is this root equals this root get right. All right. But of course, I also need to delete the root. So I need to get the and get it to a proper temporary variable. So first get me the root, and then update the root, and then delete t. And if I am the root and I am my left subtree is not null, then I need to do the same thing. So what I need to do is I need to update with my get left. Okay, I have updated the root with get left. And then what I need to do is I need to do this thing again. So let me do it like this. So this time it's node P equals this root, okay? And I need to go as right as possible. And I need to set the right to the previous right, which is still present in T. T get right. And then delete T. Okay. So because in here, probably I don't have a left child and a right child, so that's why I did it in a different way. But this is pretty straightforward. If what I'm deleting is root, then I'm updating the root and making necessary update operations. Actually, I'm thinking, can I do this by updating the child? Because this two parts seems pretty similar to me.
Hocam get right'ı yanlış yazdınız 58. satırda.
Thank you. Well, maybe it's better if I leave that as an exercise. Okay, so maybe I can make some operations, and instead of checking here if parent is null and do something, I can do the same thing in here. Yeah. Okay, please think about it. Have a look at this. I have already paid too much caution to this one. So please have a look at it if you can make this one smaller or not. So let's first let's see if it works. Let's remove 10. Okay. All right, but oh, I was asking about 10. Okay, so let me ask 6. Well, is this sorted? So it seems that I was able to do that. So let's see how it works. Let's see one by one how this works. So let's go first inside the remove 15 thing. Go inside that. Now I have taken the parent, the left child, and the right child. Let's take a look at this one. Okay, so my parent is 10. It is the root. And the left child and right child is 11 and 20. This is the left and right child of what I am removing. I'm removing 15 now. So the left is 11, right is 20. Let me remind you the 3, by the way. Let me find it first. I think this was the 3. Okay. So let me draw this one as well. 5. This is 5. Okay. So it's like I begin from 10. There is 5, 15, 11, 12. And what am I going to remove is I'm going to remove this one first. And I expect it to be like 10, 11, 20. And I am going to remove this one next. And I expect it to be 3, this sub-3 to be the child of this, and 7 to be connected to 4. And finally, I'm going to remove 10, which is going to make the 3 my new root. Okay. Let's see. Okay, so the left and right childs are correct. I'm not removing the root. So what I will do is I will first delete the node that is going to be deleted. And now the pointer of the parent is going to point to the left child, I say. So what is going to happen is I expect the root. No, it is the right child. I'm sorry, I'm removing 15. The node's right child should be 11 now. Yes. And then I will go as right as possible, which I would not be going anywhere. So I will set the right child of 11 I will update it with the 15. Is it 15? No, 20. Yeah, I will update it with 20. Let's see if it's going to happen. Right child of 11 is updated and it's 20. That's cool. So let's remove 30. 30 is not there. Let me do the removal from Y5. Okay, so let's go inside. And then now the left and right child will be the childs of 5, 3, and 7. Yep. And then I will, since the child is not null, there is something to delete. I'm going to delete the 5. And the new left child of the root will be, now this is deleted, you see, I have just deleted it. And now I'm going to update it with the left child, which is 3. Yep. And then I will go as right as possible, which is once. And then 3 is right, there is 4. I'm going to put the 7 as a right child to this. There it is. And then I will go back. Now it's time to remove the root. So you see, the important thing is left and right child is not the important one. Are they correct though? No. So the parent is null, which means I am removing the root. So if the left is not null, which is not, let's have a look at our tree. Now at the root there is 10. At the right hand side there is 11 and 20. At the left hand side there is 3, 1, 4, and on the right of 4 there is 7, there is 6, there is 9. Okay, so the left hand side is not null. What I will do is I will first get a copy of the root to T, and then I will set the root again. Now the root is 3. And the rest of the tree is just like the left subtree. So 1 on the left, 4 on the right, and on the left of right of the 4 there's 7. On the left there's 6. On the right of 7 there's 9. And I get the P, which is the right child of the root. Is that correct? No, P is the left child of the root. P is the new root, yeah. Yeah, that is correct. And I'm going to go as right as possible. So that will lead me to, I think it was 9. 4, 7, 9, yeah. And I'm going to set the right of 9 to T get rights. Data's current rights, 11. Okay, now on the right side of 11 there's on the right side of 9 there's 11 and there's 20, and then I will delete the old root. Yep. That would do the trick. Okay, that's all. So that is how you write a binary search tree. Now deletion is a painful one, right? Well, like I told you, there are different ways to do that. You can do it this way. This is one way to do it. Now I'm going to push that one into the repository, and I will continue with something different. I am going to show you how to make this binary search tree in a different way. Okay, so let me first commit those. Let me generate a new folder so that we will be able to distinguish things. Okay, so let's take those, let's put them in here. Let me open the main. Let me keep these. Okay, but I'm going to, of course, change these. Now, what I will do is, let me first explain you. It's not very enigmatic. It's easy to understand. What I will do is, I will use the node to perform recursive operations. So right now, how am I doing things in the binary search tree is, how am I doing things is, I have a tree like this. Okay, and if I'm going to add something, I take this tree as a whole, I go from the root, and I traverse the tree, and I make the necessary addition around here somewhere. Okay, now I'm going to do something different. What I'm going to do is, I'm going to prepare a special node structure for binary search tree, and what is going to happen is, when I want to add something, I'm going to just send the data to this node, and it will call the appropriate functions in other nodes. Actually, it will call the appropriate function in the appropriate child, suitable child, and then this child is going to do the same thing, and it's going to call the suitable method of the suitable child, and it will progress like this to be finally added as a new child. Okay, so instead of now this will make the functions in my tree much more simple. It will complicate a little the functions of the node, but what that will do is, that will make the node structure specialized for my binary tree. So let me do that. Okay, so let me change my node names and other things. So this is going to be binary search tree node, and this is going to be BS3. So BST node, I'm going to update those. And I am, and this, I still need these, right? Set left, set right, set data, get left, get right. I don't know if I'm going to need those, but let's keep them anyhow. And this is BST node, and about the BST tree, it's going to get the BST node, and these will be changed to BST node. So we will take a look at each of them, and which of those we need, which of those we don't. So actually, the find parent, I'm going to get rid of it, so I will delete it now. And what about those? Those will be the same. There's not much of a thing which is changing. The name will be different. It will be BS3. Yeah, the rest will be the same. Let's take a look at those. I will also rename this one over there to BS3. And I will rename this one over there to BST node. Okay, I'm just changing the names now. I will do my structural changes a little bit later. So this will be BST node. And these will be BST node. Okay, there's not much things to do. Let's take a look at the BS3. So are there any? So I'm going to delete this one over there from here. The other guys, I will need those, but let me just, for the sake of simplicity, just let me delete them. Now let me delete all of them. Okay, and if I need some of them, I will just copy paste them from my previous code. So what I'm going to take away is add contains remove. I'm going to rewrite all those. And remove contains add. Okay. I get rid of those. So let me, yeah, this should be BST node. This should be BST node. Up. And this should be BS3. I should actually make a replace. Why don't I do that? Okay, so okay. That seems like it's doing the trick. Okay, now that should work, except the, of course, additions. There is, yeah, this should be BS3. Yeah, it's compiling. Now I'm going to do my trick. I'm going to write an add function in the BS3. So the interface will be the same, I believe. So let me copy paste it from here. Okay, so this will be the same. bs3.h. All right, and let me open up the BS3 and let me copy the thing from here. Where is it? Yeah. Okay. Now let me show you how easy this would be. Okay, so this is my function, and what it's going to be is if this root is null, I'm going to construct the root, new BST node data, else this root add data I would call. And that is all. Okay, so how is that possible? I need to write the nodes data, the nodes add function. So let's do that. So inside my node now, BST node, I need to have something like void add integer. Okay, so I need to write that one. Where is my BST node.cpp? Is it around here? Yeah. So I need to write void BST node add, and it will be integer data. So how is that going to work is what I will do if my data is equal to data, I will do nothing but return. Other options are if this data is larger than the incoming data, which means the incoming data is smaller. I need to go to the left. So what I will do is this left add data. Else, or let me do it like this. Okay, let me copy this and paste this. And else, if this data is smaller than the data, then I will go to the right and make the addition. And let me put this in here, because this would be else return. I already have this. So where is the setting up the node? Okay, if it's on the left, send me on the left. If it's on the right, send me on the right. So where am I going to construct a new node? So what am I going to do is simply, I will check if this left is null or not. If this left is not null, do this. Else, this left equals new BSD node data. And the other one will be similar, but it would be with the right. And that will be all. It's that easy. Okay. So let me see what is going to happen if I make the additions. So this should be BS3 and this should be BS3. First of all, let's see if it works. I didn't write the contains function, so let me put it like this. Yes. Print in order and print BF would be good. I think it was this. Let me check. First. I have an ugly feeling that it's not going to compile. Yes. So, oh, I forgot to put the preambles. What are you saying? BS3 CPP line 20. Oh, bin S3. Oh, okay. The ugly face of copy pasting. All right. Yeah, let's check if it works, and then we will debug. Well, it looks like it's working. All right. So let's see how it goes. So this is the first case, is the trivial case of where I go inside, check if root is null, and it's null, so I'm setting up the root and going back. The second one, I check the root, it's not in there, so I add the data to the root. Of course, it's not going to add to the root, but what it will do is the root is going to, you see that this is the root, and it will compare the data with its own. And since the incoming one is smaller, then it will say it's left, add it. If I have got no left, then this should be on my left. Okay, and it returns. It's that easy. Let me also write a search function. So what did I call that? Bin-s3.h. Let's write a contains. Okay. And where is my contains? Here's my contains. Okay, I won't do the same mistake twice. And let me do the same. All right. So what I will do is return this root contains, oh, I'm sorry, contains data. It's just that. And I'm going to do the same thing. I'm going to write the same contains to the node. I had actually added it to the node definition, so let me make the correct addition here. Okay. So, and this is going to be the BS node, BSD node CPP. Where is it? BSD node CPP. So let me do the contains like this. So it would be the bool. BSD node contains int data. If this data is larger than data, and if this left is not null, so I return this left contains data. Otherwise, if it is null, I return false, which means I wasn't able to find. And just like this line is going to be return this right contains, else return false. Okay, see how this is much more easy, I believe, from my perspective. So if I find, I will return true. And let's see if that works. Right. So 30 is that in the list? No, 6 is in the list. So I expected to write me the breadth first. Printing. Yeah, it only does the breadth first printing. That works as well. Now remove. There is no easy escape for the remove, however. So it will still make us a little bit painful. And let me quickly write it as well. So let me again get the remove function from here. BST node. No, not BST node. BST3 remove. So our philosophy is calling remove for, now let's think about it a little bit. Let's not dive into that quickly. So what I expect to have is, okay. So I expect to call the remove of this function. It's called the remove function of this node. So I will call remove something. Okay, and what I expect to do is, well, I could put a parent in here showing me this, but I will try to do it as much as possible without the parent. So when I find the node which contains a link to the right-hand side or the left-hand side, so I'm going to check if the removing node, the node being removed is on the left or is on the right. What I need to do, so let's assume that I find my solution in the left-hand side. What I need to do is I need to get the left child of it and set my left child with the new, and also get the right child of it and set my right child with the new. And that will be all, except if I'm deleting the root. So, well, it seems not so hard. Let's try to do that. Okay, so I did the removing. Let me go to BS3 CPP, white BS3 remove. In data. And what I will do, so if I'm removing the root, that's a different story. So I will do like I'm not removing the node, and I will handle the remove root later. So what I will do now is this root remove data. Okay. So what I need to do, let me put that one as well in here. Now let me go to the BST node. So I can, let's close this. So contains, and that's going to be remove. No, it's remove function. All right. What I will do, I will, again, just like those, I will check the left and right nodes, okay? And if this data is larger than data, I'm going to go to the left. So if the thing is larger than data, what I need to do is, before removing, I need to check if the left's data is actually the same with my data. So that would be, now there are three options. Either if the left child or one of the childs is equal to the data, so that I will remove it, or it's not equal to data, I will continue to pass along the function calls, or if it is null, which means the number I'm looking for is not in the tree, so I will return nothing. I'll just say return. Oh, but I can handle it if in here, right? Yeah, because this is if the data is equal to my data. But I cannot do this because then I will need to have a link to the parent. I want to do the thing in the parent. So instead of writing it in here, I want to do it in here. If this left not equals null, and this left get data equals data, I will do something else. If this left equals null, I will do this. Okay, there's going to be one more line in here. So let's have a look at this. Let me put this in here as well. Let me put this in here. Okay, I can easily write here a method. So remove left or right kind of thing. So that is going to remove the appropriate child. But let me do it in line. Okay, in here, I don't want to write any more methods. So these cases, I'm going to remove this. Now this node's data is larger than the data being removed. So I'm looking to the left, and when I look at the left, there is a node in there, and this node is equal to data. So I'm going to delete your child in here, I say. So how to delete that? So what I will do is, this will be more straightforward. This set left, this left, get left, okay? But if the left is null, then there is going to be trouble. So let's keep that in mind. So I set the left to left. So now I need to go to the right node of this left as much as possible. I'm going to take this from the other code that I have written. Okay, there we go. Where am I? I'm in here. I'm in where? I'm in where? Ah, I'm in here. Okay. So that would be BST node T, and it starts from this left. Okay, that starts from this left, and it goes to right as much as possible, and it sets this right to the original children's life, right? Okay, so why don't I do this? actually I can do this. Right, I don't need to say get data because I'm already in the class. Why am I doing this? Yeah, I can do this. Okay. BST node right child. And this would be this left right. Okay. So now it would be easier if left child is not null. It's not null. Then I will do all these operations. Okay. Then I will say this. Just left equals left child. Now it's more understandable. And then I will start for the left child. I will go to the right as much as possible. And let's make this right as well. And then what I will do is I will set the right to right child. Okay, I can do it now directly because I'm in the same class, the node class. I don't need to use set left get right, this kind of thing. Okay, so else, of course, if that's not the case, then I would do this left equals right child. Right child. Okay, so this is the code. Let's do it for let's do the same for here as well. Yep. So I will call data in here, and this will be now this time it is the right child. So I will take the right left and right. Okay. So if the deleted node's left child is not null, my right would be left child, and I would start from the right, and I will go as right as possible, and then I would set the T right to the right child. Else, this right would be right child. So you see, this is still a bit complicated, and you can still do these by using the pointer tricks that we have done. So the code might be shorter, actually, but I don't want to spend no more time on pointer magic. Okay, so this should do the trick. And what about this? If this, so if I'm going to delete it, I delete it. Otherwise, I don't return anything, but I just call this left remove data. And if I'm in here, I'm just going to call this right remove data. Okay. So what is the third option? The data can be larger than mine. The data can be smaller than mine. Well, there is no third option, so I didn't write it. So what is the third option in here? The right child might not be null, and the data can be equal. I delete it. The right child, yeah, might not be null, but the data might be different, so I call the remove. Or else, right child not be null. Then this means I wasn't able to find the value, so I return without doing nothing. Okay, so let's see if that works. Now my root is 10, so I'm not going to remove 10, but I'm going to remove the other ones. Oh. Where is it? BST? Oh, is it in here? Where is it? Yeah, this. Okay, that's it. It seems like it's working. Let me make the in-order traversal as well. So let me search for 7 to see everything is all right. Yep, let me search for something I remove, 5. Okay, since we don't have a lot of time, leaving the debugging or how it works step by step, looking at these to you. Now, the last thing which we need to do is removing the nodes, and I will do that now I'm done with here, and I'm done with here. Let me do it for here. Yeah, this one. So when I'm removing, if this root get data equals data, then I'm going to remove the root, else I'm going to remove that. So I can directly copy paste my root removal code from here. Right? And I can put that here. Oh, I forgot to delete. Yeah, I forgot deletions. BST node CPP. I forgot to delete. I need to delete as well. Where am I going to delete? So, yeah, right after I do those, I can make my deletion. Yes, delete this left. And right after I do those, I can make my deletion is here, in here. Delete this right. Okay. And what about here? Yeah, that seems okay as well. The only difference is these would be BST node. All right. That seems like it. Let's do it. Let's see if that works. Okay, it seems like it's working good. 10 is no longer in the list, in my numbers. Okay, and this is another way of doing the BST. So you see, even though we copy paste a little bit, it is a little bit easier to do it this way. So what is the bad thing about it? If you do this, then your node structure is specialized for your binary search tree, so you cannot reuse it. Okay, and also you can do a lot of things like put a parent node link in your node structure, and then you don't need to do things in the parent anymore, and you directly have the access. And there are a lot of options you can do all of these. Okay, now let's have a look. I'm going to write some numbers, and we will one by one add these numbers to a binary search tree. Okay, so let me write those numbers. Now they are 20, 15, 25, 13, 17, 23, 10. Let me continue from here. 14, 19, 22, and 24. Okay, and let me add those one by one. So I start with 20. And then I add 15. And then I add 25. And then 13. Left, left. 17. Left, right. 23. Left, right, left. And then 10. Left, left, and left. 14. Left, left, and right. 19. Left, right, and right. 22. Right, left, and left. 24. Right, right. Okay, if you take a look at this, you will see that this is... Oh, I did a mistake. I'm sorry. I made a mistake. So 24 should be in here. Right? So if you look at this, this is a pretty nice looking tree. And there's a technical term for it. This is a balanced tree. So the definition of a balanced tree, even though it might change slightly, what it means most of the time is the difference of levels between its leaves. So if you look at the leaves, the depth of the leaves are all the same. So in order to go to the root, you need to make equal number of jumps. And if you are searching for something in here, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements. And if you are searching for something in here, the most number of steps that you need to take is 1, 2, 3. So it's almost logarithmic. Now, the interesting thing is coming. What I'm going to do is I am going to now write exactly the same numbers, but in a different order. Okay, so let me write those. 10, 15, 25, 24, 17, 20, 23, 19, 14, 22, 13. And let me add them one by one. So I start with 10. I go with 15. I go with 25, right. I go with 24, right, left. I go with 17, right, left. Okay, and then I continue with 20, right, left, right. 23, right, left, right. 19, right, left, right, left. And 14, right, left. 22, right, left, right, right and left. And finally 13, right, left. Yeah, that looks like it. So if you compare, now this one is not as nice looking as this, but they are completely the same numbers. So if you look at this in 11 numbers, we have, at worst, we can do 1, 2, 3, 4, 5, 6, 7. It might take us 7 jumps in order to find what we are looking for, and this is bad because we already have 11 elements. So now the order matters as much as we see, right? And how about the order is, if you look at this one, this is much more like there are lots of ordered sequences. And as you see, this is all ordered. This one is ordered, right? And if you got a lot of ordered sequences, then it's not good to use a binary search tree. Of course, if you are adding one by one. Another option is adding not one by one, but adding all together. But you do not always have that option. So it's not that you can always have you cannot always have all the numbers that you want to put in your binary search tree at once and add them as you like them. So you need to be careful about this case, how your numbers are going to arrive, how your data is going to arrive, and act accordingly. And one more thing. So there is actually, even though I speak of it like it's a rare situation, having all the numbers or all the data you want to put in your binary search tree is not a very rare condition. And there's something that we do very frequently in order to do that, and this is called indexing. Okay, so what's indexing? It's like, that's also related with your 6th homework. The indexing is whenever you got a bunch of data, probably larger amount of data in terms of unit. For instance, let me say that you have a table of students. Okay, so you are what this table does is it might be anything like a database, or it might be something like an Excel sheet. Okay, and in this sheet there are some IDs. Okay, so the very fundamental type of ID you would use is the line number, right? 1, 2, 3, 4, 5, 6. It goes like this. And inside these lines, there are some data. I don't know. It can be anything, but lots. I mean, it is a multi-parted data. So there are names, surnames, student numbers, so on and so forth, like this. So if you want to build something which is going to index those and lets you search within here, then you can use a binary search tree. Okay, and how we can do this is, of course, you can do it by, well, of course, there are other stories in here, which is if you want to find directly the row with the related ID, that would be useful to do the index over these IDs. But it can be also possible to do it using names. Okay, so, but since there might be two names at the same time, you need to handle that, but let's assume that the names are unique, or there are student numbers which are unique. So you can take all of those, read all of them at once, and build a binary search tree out of those. And in order to make it a balanced binary search tree, which is not like this, but like this, there's a very simple thing that you can do. First, you search your data, you sort your data. Let me give you the example over the numbers which I have used. So I'm sorting them now on the fly. So let me sort those. It is 10, 13, 14, 15, 17, 19, 20, 22, 23, 24, 25, 20, 22, 23, 24, 25. I think that would be all. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. And when you sort them, you know something. This is your binary search trees in order traversal. So you can build a lot of different search trees by in order traversal. But what you need to do is you want to build a balanced search tree. Okay, and if you have that information, you can automatically construct this tree. So since you got 11 elements in here, you can automatically build a tree with 11 elements, build a complete binary tree. Okay, we have talked about complete binary tree. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Now, what you need to do is when you build that tree, you can build other trees as well, still balanced, not complete, but so you see, I can put those last two in here as well. No one will stop me. But afterwards, what you will do is you will count how many elements are on the left-hand side and the right-hand side. Okay, and actually you don't need to count. You can make the calculation in an automatic way, but let's assume that you are counting. So what that one would do is there are 3 elements on the right, so this one is going to be inside the root, and do the same thing for the rest. So in here there are 3 elements. I would put these 3 elements like 24, 23, 25, and I would put the rest in here like okay, so this is going to be the 1, 2, 3, 4th element in here, and this would be 15, and this would be placed like 13, 10, and 14, and this would be like 19, 17, and 20. Okay, balanced binary search tree, quite easy, right? If you got all the information that you need to build it in your hands at once. So this kind of applications during the indexing, now you pay the price of sorting, which is something different. So you will talk about it a lot in your algorithms courses. but you pay it once, and then you search in logarithmic time in here. So if you do 1,000,000 searches, then that will give you a lot instead of searching one by one. Right? Of course, there are things like, what if I want to update my index? So what if I add another number to here? For instance, what if I add 30? So luckily 30 will be going there. But if I want to add something like 16, then I will search for it and I will put it in the correct place. But you see, I can come up with an example where the new additions can make this tree quite unbalanced. Okay, so if I didn't do that, but I might make a high range of elements in here, so there will be plenty of room to add to under 17. So I will be adding a lot of numbers in here, and the tree will be unbalanced again. So I need to rebuild my tree in order to make it balanced. And for the trees, all the challenge is doing that, building a balanced tree. Some of the algorithms try to build the tree balanced while it's being built. As you add new elements, it reorganizes so that it becomes balanced. Or you can choose to rebalance the tree, but that is a price that you need to pay. Okay, still, from time to time. So if there are a lot of additions, there are less searches, then this one is not what you are looking for, probably. So